Okay, so leaving off from yesterday, we are going to be on number 11. In the table, screenshot and explain the sum of the forces, in parentheses, net force. The sum of the forces or net force arrow for the different cases. Scene 1, Joe not pushing Mr. Fluffy here. 2, pushing the dog but not moving. And then 3, Joe pushing and the dog moving. All right, so we need to then go to our simulation. We got the dog. Oh, let me take off the bounce walls. And we're going to put on this vector. So notice right now, I'm applying a force. Right. Well, right now there's nothing. And is there a net force? Do you see a green arrow anywhere? No. So that means the net force, F sum, it should be F net, but that's what the computer is using. So it's 0 because there is no net force. Everything is balanced. Now, if I start pushing and I apply force to this puppy, right now the applied force and friction force are the same, so the dog isn't moving. And then once my applied force gets to be larger than the friction force, then we should see a green arrow of a net force. And when you see the green arrow, notice what happens. Come on. When you see the little green arrow, what now is happening? Okay, now what's happening? All right, so not a bad guess. All right, someone said that it's showing the way the dog is moving. So if I push the dog to this direction, right? Net force is in that direction. Now if I let go, what direction is the arrow? It's to the right, but the dog is moving to the left in that case. So it doesn't necessarily show the direction, but it is showing basically the net force going on in this case, what's causing the change in motion. So in the beginning, yeah, it's in this direction. It's going to accelerate in this direction. Now if I let go, it's accelerating in the left direction, meaning it's slowing down because friction force is acting on it, opposing its motion. And once it comes to a stop, there we go, we're done. Okay, so here's the dog. And now what do? We need to take a screenshot of this. So you guys hopefully remember how to screenshot from yesterday. Should do that now. So if you're observing this on the meet, you can hopefully zoom in, screenshot. Huh? That's why, don't worry about this. So you're just basically, I'm running the simulations with you guys because I know it was like pain in the butt to load. So you can just screenshot my screen. Now, on the Chromebooks, when you go to screenshot, there should be like a little window that pops up maybe down here that says like copy to clipboard. You would like click the little like writing there and it would then like copy to your clipboard to be able to post it. So I did mine. All right, so it prints, it pastes here your actual whatever the whole screen was. I don't want all of that. I just want the free body diagram. So if I double click on it, these little black borders should show up. And then we can crop this to how we need. And then click to like the side out of that little box here. And then we can click on it and expand this. Okay. So some of the forces here. In this case, we're going to say F net, the net force. So F sub, not bet, net is equal to 0. in which case that means everything's balanced. There's going to be no change in motion going on. All right, so now we got Mr. Hooper here. Joe is pushing on the dog, but his dog is not moving. All right, so I'm going to go back to the simulation, and I'm going to push on the dog. Oh, shit. Nope, we want a little less than 120. Okay, so right around here. So if you guys screenshot this right here, if everyone screenshots this so we can paste it in scenario 2 or scene 2. Okay, you can click it in here, paste this, crop it down to what we need and want. Okay, in this case, again, the fnet is going to equal is going to equal 0. And again, I'm going to literally copy this exact wording here because that's what's going on. Again, everything's balanced and no change in motion was occurring. The dog wasn't moving. Okay, and then scene 3 is Joe pushing on the dog, and then the dog is moving. Oh, Jesus Christ. Okay. So we're going to record. All right, so I'm going to screenshot this here. Now, free body diagram, guys, is basically just like a little box and that shows all the vectors coming off of it and whatnot. We'll get into that more in the next day or two. So from this, we are going to then paste. I'm going to crop this down so we get only the good. So in this case, is the fnet equal to 0? So when the F net is not 0, there is going to be some sort of change in motion. Thing is going to speed up somehow or slow down and or change direction. Okay. Okay, so now we're going to move on to number 12. Try to find 3 different ways to make the net force arrow change and explain what you did below. And then, in your own words, what is the sum of the forces, or what is net force? So 3 different ways that we can make the sum of the forces or the net force arrow change. So let's go. Let's go slow. So right now nothing happened. Then by increasing the force, I did that very, very quick in this, so let's clear that and let's record this. Slow down, dog. Come back over here. Slow down. All right, so let's clear and record. So if I start to apply force, is there a net force? There's no green arrow. So then as I increase my force, all right, I can increase the net force. If I drastically increase my applied force, I'm very much so increasing the net force. Now I'll let go. The net force is to the left because we are no longer applying a force to it. We were or was in motion, then we let go, but there was a force acting on it, and that was friction, which opposes the direction of motion and was trying to cause the thing to slow down. So we can take those kind of 3 different pieces here. Okay, you can apply force. So when you increase a force, right, and now actually have a net force, there's going to be a slight change in motion. You can see that the arrow here of the net force is not very big. The magnitude is not very big. But if you increase it, the applied force even more here, you should see that now the net force gains really, it gets a lot bigger. The magnitude gets bigger, and then the motion, change in motion is greater. The acceleration here is greater. And then if you were to let it go, the force acting on it, all right, is here. It's just the frictional force because the 2 top ones are balancing each other out. There's no force being applied anymore, but it is still moving in this direction. There is friction acting on it, which is causing the net force in this direction here. So it's causing the object to change its motion. In this case, it's slowing the object down, the dog downward. Not, you know what I mean? Slowing the dog down. So after taking a look at the different ways or playing around with on the simulation, different ways you guys can come up with 3 different ways to kind of change the net force arrow. In this case, in number 13, we're going to use the word net force to describe, all right, what causes a change in motion, a non-zero net force, an unbalanced force here. So a very good definition would probably just be the sum of all the forces acting on it. So like here, the sum of the forces, the reason why it's 0 is because the normal force and gravitational force balanced out. Here, the reason why the net force was 0 is because normal force, gravitational force balance each other out. Applied force, friction force balance each other out. Why the net force is not 0, it's greater than 0 here, is because the applied force is greater than the friction force, even though these two, top and bottom, balance each other out. So this, how would we calculate this? If we had numerical values here, let's just say 10 and 2, the net force would then be 10 newtons to the right. So for number 14, by looking at the pictures, the size or the magnitude of their vectors here, of the applied force and friction force, what they want you to describe is, all right, write down the direction you think the object is moving and whether it's going to speed up or slow down. Is the net force, what direction is the net force going to go in as well? So in this case, what direction do you think the net force is going to be? And then do you think it's going to speed up or slow down in what direction? So you guys would come up and based off of the picture and what we've run so far in the simulations, what do you think the direction of the net force is going to be? And then do you think whether or not it's going to speed up or slow down? And if so, in what direction? So guys, after you have come up with your responses to number 14, part 3, understanding force and change in speed. This, you guys, we pretty much also just ran through this in the simulation. When you give the dog a little bit of a push, and it's asking, how does the dog's speed change? If you give it a very big push, how does the speed change? And then 16 is, okay, well, using your answers, write a general statement of the relationship between applied force and how fast an object will change its speed. So I will just walk through that simulation again. And here we go. We have a little bit of a push. And there's a small net force and a little bit of a change in motion. If you give it a big push, there was a, you can see, see it for yourself. So, little push, little change in speed. Now notice one thing actually. As I'm pushing this, and there is a little bit of a net force. Now I'm not going to change the force here. What happens to the speed? Did it stay the same? So the force isn't changing, but you tell me, does it look like it's staying at a constant speed or speeding up? Yeah, it kind of looks like it's speeding up. So the net force is causing an acceleration. So that was with like a very kind of like small push, small force. Now if I did a large force, it was accelerating dramatically. No dogs were hurt in the simulation, by the way. Okay, no seals were kicked, no dogs were hurt. Although this was funny to me yesterday. We put the balancing walls on because someone was asking about it. And then we were I'm terrible, but yes, I kind of found this amusing. And we switched it to no. Then we switched it to ice because eventually he slows down because of the friction. But when we have ice with no friction, This will literally keep going. And I don't know why I'm like amused by this. Oh God, no. That's a good question. All right, can I remove one of these walls?
Oh.
Ah! He went away. No. Come back. There he is. Ah, good Lord. Oh, you know what? This is actually a good thing. You know, I'm glad you said that because now this brings into something I wanted to bring up. When there is no friction here, when you apply force to it, see a dog. Why didn't he slow down? Because there's no friction, right? When we push the dog in the other case on wood and we let go, you still see that there is a net force here, yeah? Which means there is a change in motion. It was causing it to slow down in this case because it was going in the direction opposite of motion. All right, when the net force is in the same direction of motion, there is an acceleration. Now it's slowing down. Come back. Good boy. But now if we just do it with the ice, and we just even give him a tiny push, as soon as we let go, the net force is gone, but the dog is still moving. So this leads us into something we're going to talk about right after this assignment. There are two types of equilibrium, which means when the net force is equal to zero. One, when it was at rest, right? Everything was balanced. It wasn't moving, which is what we saw. And then in this case, all right, we got it up to a certain speed and then let go. Now the dog is going to move at a constant speed in a straight line. The net force is equal to zero. So it's technically, by a definition, which we're going to talk about, called dynamic equilibrium, that is when an object is moving at a constant velocity. So straight line, constant speed, the net force is zero. All the forces balance each other out. In which case, right, it had the normal force. We saw it. We still have the normal force and gravitational force, and they're equal to each other in opposite directions, so they balance out. There's no friction. There's no more push force. So there's nothing now causing this thing to change its motion. There's no unbalance. There's no resistance to whatever. There's no little little arrows on the ground like in Mario Kart that cause it to speed up or anything like that. There's nothing slowing it down. All right. So with all of that, you guys should have been able to fully fill in everything. And when you have completed, all right, and got all your answers in, make sure that you guys submit your assignment.